Hello, this is Questionable Coding with Vladimir. Today we're discussing a very interesting data structure called Trie. Trie is a very good example of us naming things in a wrong way. It's very similar to Trie. It's hard to distinguish one from another. It's hard to understand how to pronounce it when you first see it in an article, let's say. And Trie is based on the tree, but it's a very specific data structure. Because of that, it's not required to know when you just approach your first interviews. It will be available for you later on when you discover all standard data structures, because Trie will be useful in a few specific cases, as I already mentioned. Let's say we have a big text and we are asked to find if a specific word is there in the text in a very efficient manner. So one of the ways to implement it is to use a hash map. So we are going through the entire text and we are adding word by word, we are creating a hash table where each key is a word, or a hash of the word, of course. So it will help us a lot. It will be a constant lookup, and it will require space, like n space, where n is a number of characters. Cool, that's already a very efficient way to do that. Maybe it's completely enough for this specific task, but what if we are also asked to find if there are words which start with a specific prefix? And it's extremely hard to do it and inefficient to do it with a hash map, a standard one. Because when you have a hash of a word, you rely on the entire word. If you have only part of that word, you can't correlate one hash with another. You can't understand if there are words that are starting with this specific prefix. And for the Trie, the implementation is different. We will go through the entire text and one by one, word by word, we'll insert those words in our tree, where every node is a letter of a specific word. And it will help us to navigate through that tree if you have only a prefix. And we'll see how it's done when we'll practice that. Okay, so we have a Trie. Sometimes it's called prefix tree because of what I mentioned. Sometimes it's called digital tree. It can work with text. It can work with binary data, with any data that we can divide in tokens or in characters, in symbols. So let's see how it's implemented and how we can use it to benefit from it to solve our tasks that are specific to this data structure. I think we should start with a cool exercise. So we have a couple of words, 5 of them on the left: or, damn, on, do, or. We have root, an empty root where we'll start our Trie. And we'll try to imitate an algorithm. So we'll take word by word and we'll move symbol by symbol to the Trie, same way the algorithm will do it. There's a small note about the words. Every word ends with a letter which is marked as with asterisks as an end of the word. It will help us a lot when we construct a Trie, but maybe a little bit later on. So right now we just remember that this symbol ends a word. Okay, let's first take the first word, or, and our root will start with root for every word, and we'll start symbol by symbol. So first symbol is O, and we check if our current root has such child. It doesn't, so we move it here. I'll leave some space because we'll have multiple branches. So this will be a sub-branch of the root, of the first branch of the root. And then we are working with O, it's our current node, and we check if there is a child R of O. There is no childs, so we just create a child R. Same with R, we check if there is a child E. There is no child, so we create this node, and now we have a branch which completely describes a word or. Cool, let's take another word, damn. We start with root once again, and we see if there is a child called D for the root. There is no child, so we create a second branch from the root. And now we work with D. We check if there is a child A. There is no child, so we add it. Same with M for A. I'm not drawing arrows here, but imagine that from root to O to R to E, there are arrows, and the same for the second branch. Okay, now it becomes tricky. So we have word on, short word, but it will bring some diversity to our process. We start with the root and we check if there is a child O, and there is one, so we're not doing anything except maybe making it active node. Yeah. Now we're looking if O has a child N, and it doesn't. That's why we need to create a sub-branch. So basically we are moving it here just to have a visual distinction, and we have two branches for O. Nice. What about the next word? The situation is similar, so we have root and we have D, which is already a child of the root. So we are just ignoring it and making it a current node to investigate. So for D, do we have the child O? No, we don't. So we are creating a sub-branch the same way we did it here. So I'll move it here. It will be a sub-branch for D. And the last one, or, it will cause us some problems, even though it looks similar, super similar. So do we have O in the root as a child of a root? Yes, we have. We can ignore it and make them an active node. And do we have R? Yes, we do. But is there a difference? So here we have R as a middle letter of a word or, a 3 letters word, right? But we want to know that we have also a word or, 2-letter word. That's why we need to mark it as an end of the word. So now we know that here we have two different words because we have two asterisks here, and if we go from root, we first have the letter O, then we have a whole word or we'll continue and have a 3 letters word or. They sound very similar, but yeah, that's what we have. And we have a tree, and we combined some letters that were exactly the same. If a couple of words started with the same prefix, we combined those. We didn't duplicate those prefixes, but for the rest we just created a new node. Now let's discuss how to implement nodes. Node is pretty simple in the trie, but it can vary. So some nodes can be bigger. For example, they can include additional data like counter, how much this letter appeared in all words that were inserted in the tree, or for example the reference to the parent. So we can address our parent from our current node, which is not very usual for standard tree, right? Because tree, it's like one direction data structure. Okay, but the main point is, how do we represent children? How do we represent that some node has a number of children, other letters? For that, we're using one way to do it is to use maps. Let's see how it's done. So we have a node, we have a constructor. We don't care about other parts of the constructor, but the main point is that children are equal to an empty map. So when we want to add some other node, we just say that, okay, children with the key O has another node inside it as value, and this another node will be R or N, as we see on the picture. The second way to implement it is to use arrays, and it looks a bit harder, and I think it shows the real picture that there is an overhead. When you are using arrays, you need for every key to represent its children, you need a fixed array which is equal to alphabet size. For example, if you have, let's say, alphabet of 30 letters, there will be 30 empty spaces allocated for every key that you have. And for example, here for the first level we only use O. It's our middle of our array, but we assume that all other characters also consume space, even though they are not there. And some people are using that approach. I'm not a fan of that approach, but it's used. So basically, when you're checking for some letter, you need to convert it to an array index, and the A will be the first. I click the button, so we see it on the right how we'll represent it. The children will have an array, an empty array instead of a map. It's very similar visually, but there's an array. And if we want to check for a letter, let's say we have letter A, we need to convert it to an index of an array. So here we'll have index 0 for A, index 1 for B, and there should be logic that does that. It's a very common thing to do, but still you need to understand that it's not just mapping character one-to-one, it's converting it to the index of the array, and we'll consume more space because we'll have space for the entire alphabet for every key. But we treat it as constant space, so even if it's like 30 symbols alphabet, it still will be a constant value for us, and we'll ignore it when we'll think about complexity. So how can we mark a word? We didn't cover this case, we covered only the second case, so let's start with a new one. Let's say we have a word or a symbol N, and we need to mark it as the end of the word. And for that, we can add a special child to that node. And how will it look like? So we have this constructor node. It has this children. We already covered it before. What we're going to do here, we're going to add this child asterisk, and we'll set it to true. It can be anything, the value can be anything. We just need to be sure that it's there, it's among the children, and we know that our current node with that child, it will end the word. I'm not a big fan of that thing, because we are mixing concept, we're mixing nodes and those special kind of nodes, and I would prefer to do it the second way, but still it's a legit way to do it. The second way of doing that is what we used before. We just have a node and we have a property, special property for every node that can mark it as a word or not. Of course, that requires allocating memory for that, for every character or every symbol or every node that we have, even though maybe most of them won't be the end of any word, but it looks like this. So we have this constructor children as before, and we have the property is word, which is false by default, but then we can mark it as true, or we can have it as part of constructor, of the signature of our constructor. It doesn't matter much, but still the idea is just to use another property. There are multiple operations with trie. There are some of them. Standard insert that we already did, contains, which is similar to insert. We just go through a given letter, a given word, letter by letter, and we check if there are such nodes in the tree or in the trie. Remove, if you want to remove a word, and there are some optional things that may be crucial for your use case. For example, if you want autocomplete, you'll probably need get all with prefix. So you have a prefix, let's say on, and you want to follow that prefix in the trie and then traverse the rest of the trie to get all words, or maybe a limited number of words that start with that prefix. And starts with, we could also call it starts with prefix, is just finding that there are some values that are after a given prefix. It's not about traversing the entire part of a tree, but just following the tree, the same as we do with contains, but maybe even simpler. Here goes our final part. We'll try to introduce the node, we'll introduce the trie, and it will have a couple of methods. The first one will be insert, where we'll just insert the word. And another one will be contains. And the last one will be starts with prefix. So let's start with the node. It's pretty simple. The node implementation can be different, as I already told you, and we'll do the smallest node that we can. For that, we'll have a small constructor and two parameters. The first one will be children. We'll use maps for that, so I think that will be much easier. And another one will determine if this symbol or this node ends a word. So it will be his word, and you can call it in a different way. The main point that it should be clear that it ends the word. Okay, that's all that we want to have here. Now we're going to build the trie. The constructor will be even simpler. It will have only one field, and it will be root. And it will be an empty node. Now let's work on the methods. The first method will be insert. And it will have a word in the signature. We won't have any checks that the word is really consists of characters. It can be a number, and of course that won't work, but we'll assume that we're giving the right data. So first of all, we need some current container for our current node. And we'll start with root. We'll initialize our current with root. Then we'll iterate through the word. I'm using the simple for loop. And in every iteration, what we're going to do, we're going to check, first of all, let's create a variable for our character that we try to insert. It's not required, but just for readability, we'll introduce it. Or chart to insert. And that will be word I. Now we're going to check if it's already a child of our current node. So if it's not, then we'll act. So if our chart to insert not in current children, then we want to what we want to do? We want to add an empty node there. So we'll say that current children character to insert, it's our key. It will have an empty node. After that, we are going to change the current node to update it. So basically, we'll update it to what we just added. Or if we found an existing node, we'll update it to that existing node. And after all, we want to mark it as a full word. So what we're going to do, we have current still here, and we'll say that is word equals true, because that's the end of our word. Right, so we have insert method, and good news are that we are going to reuse this method in our future methods. So the next method will be contains, and it will also have a whole word. So in this case, the hash map will be much more efficient, because it will just have a hash of the word and look it up in a constant time in a hash map. Okay, for contains, what we're going to do here? We're going to do the same thing. I'm just copying the implementation to save some time. So we have our current node. We start with root, and then we are also iterating through all the numbers, through all the letters. Let's just copy everything here and update it, and I'll comment what we are going to update. So first of all, we're going through the entire word. Then we have a different container name. So instead of character to insert, we want to use character to find. Let's update it. Okay, if we couldn't find a child, then we will return false. It means that the word is not there because our path can't be continued from that moment. So we will just return false. It's our first major difference. Then we should also update our current node because we're going lower and lower in the tree. And in the end, we don't want to mark it as a word, but we want to check if the last node that we reached without failing is the word. Because it can be that we went through the entire word that was given, we found all the letters, but the last letter is not the end of the word. It could be just some letters that are part of a bigger word. That's why we want to make sure that it's a word. What we're going to do, we're going to return that current is our word. And yeah, before I was using a wrong property here. So is word end. And here we return that it's the word end. Cool, we have contains method, and now we can do starts with prefix. It's even simpler than the first one, but very similar to that. So let's say starts with prefix. And for that, we're giving a prefix. So it's not the entire word, but a part of a word. So let's say we have the same thing. So I'll just copy it here once again. And let's go through the entire array once again. We'll copy it, not the array, sorry, but the word. So we're giving prefix, and here we use word. I'm removing the word and changing it to prefix. What else? So we're going through the entire prefix character by character, and we see that we have a container for each character, just to name it properly. Character to find, that's perfectly fine. What we have here, if we didn't find a character, we also return false. It means there are no words starting with that prefix. And we're also updating the current node. But in the end, we don't care if it's the word end. We have a prefix, and if we reach the end, it means there are some words lying below that are real words. So we just return true here. So if we didn't fail when we searched character by character using our prefix, then everything is fine and we return true. You see that there are some parts that we constantly repeat. I think we can encapsulate them in some method and reuse it, but right now it's perfectly fine. So that's how you can implement some simple and basic methods of a trie. I hope it was useful. So stay tuned, please subscribe if you didn't do that yet, and I'll be glad to cover new data structures. It's been a while since I did the previous data structures video. I think I will research more. Maybe you have something in mind, maybe there is some specific data structure that you want to research and it will be useful for you, also for me. So yeah, please mention them in the comment. I'll try to spend some time and to research them to prepare some presentation for you. See you next time.